we're going to look at derivatives and how they help us to understand the shape of graphs. So let's start with this fella. Here's a basic function. It starts at x equals -5, it finishes at 17. It's got a nice kind of polynomial curve going on. Anybody remember what those funny little peaks are called? Starts with the C.
Cusp.
Right. So the little cusp here. There's a local minimum here. There's a local minimum here. There's a local max. It's got all the usual features. And what we're going to do here is just talk about the terminology and how you would write things down. So the first two terms are things that you've met in 141. So we're just kind of rehashing it. We talk about a function increasing and a function is decreasing. Right? A function is increasing when, if you travel from left to right, you go uphill. That's how I think of it. So the function here, it's increasing from x is -5 to here, which we will say is -2. And you will write down the interval on when it's increasing. So anywhere between x is -5 and x is -2, the function is increasing. And then at this point here, up to that cusp, as you travel from left to, I think of it like you're moving from left to right. If you go uphill, the function's increasing. And if you go downhill, the function is decreasing, right? So it's increasing here as well. And that's what, from x equals 2 to 7. Now that is not a coordinate. That doesn't mean the coordinate's 2, 7. It means x starts at 2 and x finishes at 7. It's an interval of values, right? Does anybody know what the curved brackets mean in interval notation?
They go up to that point, up to 2.
Yeah, but not
7.
Yeah, but not using it, but not included, right?
Oh,
if you want to include it, you would put a square bracket. So here's your first little trick. You'll never use square brackets on these. Technically, you could, I guess, if I'm being pernickety, do that. But to be honest, most people do that because you're not quite sure what that function's doing there. And at this point here, and all the way to the end, this function is increasing. In this case, what number is that meant to be? I guess I wanted that to be 11. I wanted that to be 7. And so what, 11 to 17. Now, what you would normally do, but you don't do this in WebAssign, is you would normally put a little union symbol between each of these intervals, just to say that the whole thing is like tied together. So this function is increasing for values of x between -5 and -2. And then there's a bit of a pause, and then from 2 to 7, and then a little bit of a pause in 11 to 17, and that would be increasing. And it's not a surprise that decreasing would be this guy. And decreasing would be from -2 to 2, and then there'd be another decrease here, which is what, 7 to 11. And we would do that. So what do they do in WebAssign? You do the interval. You just do a comma. I don't like that, but I guess for whatever reason they did that. So see this guy here? Interval, union, interval, union, interval is interval, comma, interval, comma, interval. It's really ugly notation. I wish they would figure out how to put those little union symbols in. It just would be so much more mathematical. Are you happy about a function increasing and decreasing and how you would describe the interval of values where that's happening? Going uphill, increasing, going downhill, decreasing. Going uphill, increasing, going downhill, decreasing, going uphill, and so on. Now, this is a term you may or may not have heard. Concavity. We sometimes describe a curve by using a term called concavity. It really just means how curved is it and what kind of curve has it got? And there are only two kinds of concavity. Concave up, which are ones that look like happy faces, and concave down, which are when the curve looks like a sad face. But it doesn't need to be the, both sides of the happy or both sides of the sad. A function can still be concave up if it's only got one side of the smile, and it can still be concave down if it's got only one side of the frown. So in this shape here, the one that I've drawn here, from here to here, this piece here, back to what color? Red looks like good. And this piece here, this guy is concave up. So that's from -2 to 3. This curve is part of a happy face. So if you're part of a happy face, you're concave up. If you're part of a sad face, you are concave down. Is there any region in this picture that you can see that we would describe as concave down?
Five to 12.
So we're saying 5 to 12. I understand why you got 5. I do like the 12, so I'm keeping that. But I'm going to show you a little bit of a problem that we have with concavity. I think everybody would agree that this green bit that I'm trying to draw in is definitely a sad face, right? Can you see the sad face? Unfortunately, isn't this guy here a happy face? So isn't there going to be some point where the happy face meets up with the sad face? And you see it's not at 5. Would you agree that this bit here is more part of a happy face and concave up than it is a concave down? So what you have to do is you have to make a little bit of a judgment call. So I'm going to make the judgment call that it's happening here at 7. So this shape is only going to be that much of it is the concave down part. And that's going to be from 7 to 12. And this piece here is happy face again. So that's concave up. So what's that going to be? It's going to be from 3 to 7. Now, you might argue about the transition point. You might think, it looks more like it's 8 to me, or it looks more like 6. You're never going to be able to say, oh, the transition point is 7.1234. Would you agree? You can't look at a graph and get that kind of specificity. So keep to whole numbers and keep to roughly the middle, right? Now, we even have a special name for this transition point, and it's not called a transition point. It's called a point of inflection, right? And the point of inflection doesn't get an X and an interval of X's. It's a single point. So I'm going to pretend I know where that is. And you write down its coordinates. So this is one of the situations where interval notation is a bit clunky. When I write this down, don't I mean an interval of values from -2 to 3? When I write this guy down, don't I mean the single coordinate 7, 10? But when you look at it, don't they both look exactly the same thing? Right? So I guess we just don't have enough brackets in the world to give intervals a different bracket from coordinates. And how do you know it's an interval and not a coordinate? If it's a point of inflection, it's a coordinate. If it's an increase, decrease, concave up or concave down, right? Everything else is an interval. It's that, right? You talk about concave down, you're talking about an interval of values, right? If you're talking about a point of inflection, it's a single coordinate, and you just have to live with that. So, are we happy about concavity? Shapes being concave up and shapes being concave down. Right, so let's look at how that works out when you do it on, when you do it on WebAssign, because The first couple of, I think it's the first two, but it might be the first three questions. Oh God, I got a joke just came here. Got to tell you it now. Did you know that Hitler was Irish? Yeah. They found his original birth certificate and he was born in Ireland. And his name wasn't even Adolf. His real name was Richard Potato. That was his real name. But when he moved to Germany, he changed it to Dictator.
All right, that was a good one.
I'm getting the head shake off Zoe. What was the head shake about?
It's terrible.
Terrible good or just terrible?
Both.
Okay, I'll take what I can get. I thought that was a good joke, but what do I know? Of course, I've totally lost the place, and probably so have you. So let's. Where the heck am I going? Oh yeah, we're going to look at WebAssign, right? Hopefully, are you looking at WebAssign? Right. So we'll get that thing out of the way. Right. I can't move my mouse pointer on it because it does all this writing. So I'm just going to have to look at it and talk about the numbers. Right. Tell me an interval of x's in that picture where the function is increasing.
1 to 3.
I agree. We'll assume that 0 is the beginning and 6 is the finish of this function. So tell me another place where it's still increasing, another interval.
4 to 6.
Okay, when's it decreasing?
3 to 4.
Okay, that works for me. Tell me an interval, this is a bit trickier. Tell me an interval when it's concave up.
0 to 2.
Agreed. Would you agree 2 is probably the transition spot, right? It's kind of halfway between the 1 and the 3, right? It's probably in the middle, right? So that would be concave up. So tell me a concave down.
Would it be 2 to 4 or
Yeah.
2 to like 3.5?
No, we'll do it 2 to 4. Right, all the way to the cusp, right? All the way. So from the interval from 2 to 4. There's one more concave down. Where is it?
4 to 6.
Right. Now, it's kind of hard to see when it's only part of a happy or sad face, isn't it? Because you don't really, you got to imagine that curve continuing. Now, it might curve round and eventually become a very noticeable sad face if it was given the chance. But even if you're only one piece of the smile or one piece of the frown, you still count, right? You're going to be concave up or concave down. I guess unless you're a horizontal line, but we won't talk about those, right? If you're a curve, you're going to be one or the other. You have to be. So whichever one kind of makes sense is the one you should do. Okay, here's another one. Give me a decrease, an interval where this function is decreasing.
0 to 1. Sorry, decreasing 1 to 3.
1 to 3, right? 0 to 1 would be increasing, as you're correct. Give me a concave up.
2 to 4.
Yeah, I think 2 to 4 looks more natural. What's happening? Let's phrase it a different way. What is happening, concave up or concave down, in the interval 4 to 5?
Concave down.
Yeah, isn't it one side of the frown? What's happening from 5 to 7 now? Concave up or concave down, 5 to 7?
Concave up.
Concave up.
Concave up. Are we comfortable now about concavity up and down? If I asked you for a point of inflection, right? Right, so a point of inflection is a transition between a concave up turning into a concave down. Give me the coordinates, and it's a coordinate now, of a point of inflection.
0, 5.
I was gonna say 4 to 3.
Well, I hear 4
Yeah.
3, and I agree. I think you meant to say, well, I'm not sure what you meant to say when you said 0 5.
5,
0.
0.
5 0. No, 5-0 is on the x-axis.
Oh, sorry. I meant to say the one area
At
where it
5.
was flat. Yeah.
Yeah. So the 0, I guess you might have been talking about derivative then, but the coordinates is at 5, 4. Would you
I'm
agree? a
still
happy
in tangent lines.
Yeah, your derivatives. So 5, 4 is a point of inflection. Isn't that a happy face turning into a sad face? A concave up turning into a concave down, essentially. 4, 3 is a good one. There's one more. Find the last one.
2, 2.
2, 2. We got them all. So if I gave you a curve, a nice polynomial curve, or maybe a little cusp in it, do you feel comfortable about all the increase, decrease, concave up, concave down, and point of inflection, right? We're just getting used to the terminology of how you describe the shape of a curve. So let's leave that and talk about how can derivatives help us with these kinds of things. Okay, let's talk about derivatives and increasing, decreasing. So is there a connection between the value of a derivative of a function and whether a function is increasing or decreasing? And the answer is yes, that is a very simple connection. A function y equals f of x is increasing when its derivative is positive. And it's decreasing when its derivative is less than 0. It's negative. Let's see how that works. Right. Got this guy here, right? The original one. Take that fella there. You see this piece of the curve from here to here? Would you agree that if I did a tangent line at any point on this curve, wouldn't that slope be a positive? It would be pointing up the way. And for decreasing with the green ones, would you agree that the slopes are pointing down the way, so it's negative? So we now have a way to use calculus to find out if when a function is increasing and when a function is decreasing. Let's give you a very simple example. Suppose I had the function x cubed, take away, I want 4. Yeah, that's easy to work with. So what I had the function x cubed minus 12x. I'll just write it again because it looks ugly. If I find its derivative, which is 3x squared take away 12, and then I do style points. I get that. Great. So if you want to find out when is a function increasing or decreasing, like for this cubic, for instance, first thing you're going to do is find its derivative and factor the heck out of it. Now, the reason why you're going to factor the heck out of it is because isn't it easier to solve when is the derivative 0? Because when you find out where the derivatives are 0, that's going to be the start and the end of the increasing stroke decreasing situations. So this fella, right, is going to be 0 at x equals -2 and at x equals 2. So far, so good. Now, what I tend to do here, and I'm a visual person, but there are other ways to do this. is I draw a number line. And on this number line, I'm going to put values of the derivative. Now, I know that when x is -2, the derivative is 0. I now know that when x is 2, the derivative is 0. And what these guys do, by the way, these are critical numbers. So you know what those are anyway, right? These guys here are critical numbers. Well, what they do is they separate the x coordinates into places where the function increases and places where the function decreases. So what I do now is I basically just take a test point. I take one number from this interval here. Can you imagine a little invisible dotted line, a little wall here? And so I've got 3 distinct regions. And on this region here, I pick one number, -3 will do, and I find out what the derivative looks like. So if I cover this up, because it's a distraction to me, when x is -3, can't you plug it in here and find out if the derivative is positive or negative? So maybe I should just write it down here so I can work on it. Here is our derivative. And I'm going to test what the derivative is at -3. So it's 3 times that guy times that guy. Would you agree that this fella, oops, is positive 15? If I've done it right. 3 times -1 times -5. Yeah, positive 15. That guy is positive there. And here's the clever part. So's everybody else. So my function is increasing for any value of x that's less than -2. Now, what about this second region? What do you think might be a good choice for a test value for x? Because whatever value we get, plus or negative, all the derivatives are going to be the same thing. So if this is plus, everybody's plus. If this is negative, everybody is negative, right? So what would be a good test point?
0.
Yeah. Now, here's a shortcut that I like to use. I don't really care that the answer was 15. All I really cared about was that it was positive, right? So when I do these calculations, I don't actually do numbers. I do signs. 3 is positive. 0 plus 2 is positive. 0 take away 2 is negative. Won't that combination get me a negative answer? And so I don't care if it's plus 52 times -43 plus 712, because that's ridiculous. Don't I just care that the whole thing's plus something or the whole thing's negative? So that makes this fella negative. It also makes everybody else negative. And then over at the end, I think I'd probably pick 3 here for the end. Right, 3 is positive. 3 plus 2 is positive. 3 take away 2 is positive. That makes the whole thing positive. This number line with all the pluses and minuses in it is everything pretty much I need to know now. For instance, isn't the function increasing in this interval? Why do I know that? Because the derivative is positive. What's it doing between -2 and +2? What's the curve doing? Increasing or decreasing from -2 to +2?
Decreasing.
Right? And what's it doing up here?
Increasing.
Increasing. Oops, right. So if you want to know when a function is increasing, well, anything that's less than -2. Now, since this didn't have a start value, all you put in is -infinity. And then on this side, 2 infinity. And when is it going to be decreasing? Well, any value of x between -2 and 2. So this one number line contains all the information I need about increasing and decreasing, but I can do better than that. I can even tell you a little bit about the shape. If you can visualize it, a function is increasing, then its derivative is 0, and then it's decreasing. Wouldn't it look like that? Increasing, going uphill, 0 at the top of the hill and down. So can't I even tell you that at x equals -2, isn't there a local maximum? And on this side here, right, at x equals 2, it's decreasing, then it goes 0, and then it's increasing. Can I now also tell that there's a local minimum? Do you see I get local max and local min for free? Right, they're already in that piece of information. So far, so good. Yeah. If I wanted to do a very, very rough sketch of this, wouldn't it look like that? Which is exactly what cubics should look like, right? Cool. Now, that's how you find out when a function is increasing or decreasing, right? Right. Check, check, right? That's us two. Wouldn't we like to know concave up and concave down? Wouldn't that be nice? Right. Is there a way that calculus can tell us, right, concave up or concave down? Now, if the first derivative tells us increasing and decreasing, would it surprise you that the second derivative tells us about concave up and concave down? And it does. So here it goes. A function y equals f of x is concave up when its second derivative is positive. And it's concave down, right? When its second derivative is negative. So I think of it as positive second derivative concave up, negative second derivative concave down. So far, so good. So let's take that function that I used a minute ago, the x cubed minus 12x1, and see when is it concave up, right? And when is it concave down? So the original function was that, and we already found its derivative, which I'm just going to rewrite like that. And now I'm going to find its second derivative. And all I do is I solve for when the second derivative is 0. Basically, I just find the critical numbers of the second derivative. And in this case, it's such a simple question. Can I just say it's 0 because it's pretty obviously yes. And I draw a number line. And I put 0 in it. And this number line is all about the second derivative. So just to remind you who the second derivative is that guy, right? Now at x equals 0, the second derivative is 0. That has essentially split the x-axis into two distinct regions. And on this side, it's either concave up or down, and on this side, it will be either concave up or concave down, right? We're going to find out which. Okay, so how do you think I'm going to find whether it's concave up or concave down on this side here? Well, think about what we did when it was the first derivative. Didn't I just pick a point? How about -1, because it's easy? So the second derivative at -1 is definitely negative. So this guy is negative, and so is everyone else. And how about 1 on the other side then? And that's definitely positive. So what we have here is, since it's positive, so is everyone else. So I can now do concave down, and I can do concave up. It's concave down for any value of x in this region. So that's basically -infinity up to 0. And it's concave up anybody in this region. And the last piece of the puzzle, point of inflection. What will be the x coordinate of this point of inflection?
0.
Agreed. And then its y coordinate will be whatever you get in here. Oh, pretty boring. Happens to be the origin. So on this side, can you see concave down kind of thing here? Whoops, can't do concave. Concave up here, concave down here. If I do my really bad version of it, that guy there is the x equals 0. Can you see the concave down and then the concave up? And that's what's being reflected here. So we can find essentially all the good stuff by using derivatives. Can't we find where it's increasing and decreasing? When is it concave up and concave down? And even points of inflection. We can find all of them, right? Everything. And that's kind of what this section is all about. Finding everything. Now, we're going to look at how to use the graph of the derivative function. To understand the graph of the original. So we're going to look at how do you use the graph of the derivative function f dashed of x to understand increasing, decreasing, points of inflection, right? All that good stuff. Well, I want you to, and you got to keep your head on here. This guy is not the original function. This guy is a graph of the derivative function. So you imagine you got a function and you differentiated it and you put it into Desmos and it looked like this, right? You can use this graph to figure out what the original graph is doing. So let's say that guy there is 1. Let's have that as 3. Let's have that as 5. Let's have this as 6. Let's say that's 7. Yeah. Have that as -1. I know. have that as 10, right? I think I've got all the key numbers. From this graph, I can tell you the intervals in which the original function, f of x, is increasing or decreasing. Right, so remember, this is a derivative function, not the original. So won't this function, the original function, be increasing when the derivative is positive? Agreed? Positive derivative means it's increasing. So isn't it increasing from 1 to 5? Where else is this function positive? Where else is the derivative function positive?
Seven to 10.
Right? So do you see I can use this to tell you where the original function is increasing and decreasing, right? It's increasing from x is 1 to 5 because it's positive. It's increasing from 7 to 10 because the derivative positive above the x-axis, right? That's where the positive values are. In the same kind of vein then, isn't it decreasing from -1 to 1 and also from here to here, which is what, 5 to 7. Can you see how a graph of the derivative can tell me what the original function's increasing and decreasing regions are? Get a little extra benefit here. Let's look at what's happening at x equals 1. If you just focus on x equals 1, which is here, the function comes down here, right? The derivative, and then it goes up here, right? Now, at that point there, isn't the derivative 0, right? Because this is the x-axis. And these guys down here, isn't it negative? And then this guy's up here, it's positive. So let's see what that looks like. It's decreasing, 0, and increasing. Oh, doesn't that mean that this fella here, right, at x equals 1, isn't that a local minimum? Would you agree? At that point there, negative, right, decreasing, 0, increasing. Decreasing, 0, increasing, right? It's got a, whoops. I'm not hit things. I'm going to hit things. Don't hit things. There. Are we cool with how I did that? Okay, look at 5. Positive, 0, negative. Positive derivative, increasing. 0, negative. Oh, does it not make this what we call a local max? Okay, what's happening at 7? Local min or local max?
Local min.
Okay, and let's check it out. At 7, isn't it negative on this side, positive on that side, right? That's what it looks like. Negative means decreasing, 0, flat, and up. Can you see a local min again? Now, this is what kind of information you can get from a derivative function. Can't you get increasing and decreasing? Can't you also find out local maxes and local mins? There's only one thing missing. I'd like to know concavity. I would like to know, in particular, points of inflection. This shape, this derivative function, is telling me that there are 2 points of inflection. Now, it only tells me the x coordinate of them, right? The y coordinate you could only find out once you knew what the function was called, right? But I can tell it has 2 points of inflection. Can you tell me the x coordinate of either of them? Now, a point of inflection is where there's a change.
Where it changed, right? 3 and 6?
Yeah. Exactly. So when you look at derivatives, you have to have a little hat on. This is my hat when I'm looking at f of x. I have a different hat, a derivative hat, when I'm looking at a derivative function. And so if I can see a derivative function, wouldn't that point there be a change from an increase into a decrease? And wouldn't this be a change from a decrease to an increase? And isn't that where points of inflection happen? Points of inflection happen when the second derivative is 0, right? And isn't the second derivative 0 at the tops of hills and the bottoms of valleys of a first derivative? Do you see how they're kind of interconnected? Now, I have made an assumption all the way through that no one has disagreed with, I guess, because you just trust me. And I remember when I did a test point, I said, okay, we only need to test this one. And if it's positive, everybody's positive. And we only need to test this one. And if it's negative, everyone in this region from here to here has to be negative. And I just said that, and maybe it's kind of obvious that it's true. But here's the reason why it is true. We've already found all the critical numbers for a function, right? We've already found all the places where it's 0. If your function is continuous and differentiable, so what we've been doing right now has always been for nice smooth curves, right? Nothing weird, no piecewise, nothing weird, right? If we found all the places where the derivative is 0, these have to be positive, because if some of these were negative, wouldn't there have to be a point where a plus turned into a negative? Now, the only way you can go from a plus to a negative, right, from above to below, isn't it to pass through 0? And since there are no more zeros, once you know one guy in an interval, everybody in that interval has to be the same guy. And that's kind of the logic behind why we're allowed to do all this cool stuff. If that wasn't true, really, this would be a pointless exercise, right? You wouldn't be able to use it. Have we learned some cool stuff today? And regardless of what certain people have said, my joke was good today. I don't care about, it was good. Okay, let me click out of this for a second. We've got a few more moments, so let me show you what that looks like as a homework question. Here is the derivative function sketch, right? They're I can't do it. They're starting at 0, finishing at 6. Okay, tell me an interval where this function is increasing.
Did you turn it on? We can't see it.
Oh, sorry. Yeah, say hi, by the way, while this is happening. Good idea. You can't see it now?
Yeah, we can see it now.
Okay, phew. Okay, give me an interval where this function is increasing. The original f of x is increasing.
0 to 1.
Agreed. Give me another interval where it's increasing.
3 to 5.
Okay. Give me one interval where it's decreasing.
5 to 6.
Yep. And another interval where it's decreasing.
1 to 3.
Okay. Tell me the x coordinate of a point of inflection.
2.
And give me the other point of inflection's x coordinate.
4.
4. Do you see how much information is contained inside a derivative function? You know an awful lot about the original, even though there's no indication of what that original is. We can still have a fairly good guess at what it looks like, based on only what its derivative function is telling us. I haven't the time, and hopefully I'll remember to do it. What do you think a second derivative function tells you? So if I showed you a sketch of f double dashed of x, what kind of information would you get about the original function from just that?
Where it's concave up or down.
Yep. And won't it be concave up when the second derivative is positive? And it will be concave down when the second derivative is negative. Where will the point of inflection happen?
It's at 0, isn't it?
At 0. You don't get that much out of a second derivative. You can do the concave up, the concave down, and where the point of inflection is, and that's kind of it, right? You don't get much more than that. And perfect timing. So bye-bye, because you've already said hi, I hope.